Welcome to Code with Vinay. In this video, I'll be discussing how to test if a given integer is a prime number or not using recursion. In other words, we'll be exploring a recursive primality test. Just like many other videos on this channel, we'll first discuss the regular approach and then we'll optimize the code to make it faster and more elegant. After all, who wants to run a slow and inefficient program in real life? I've already discussed the iterative primality test in one of my earlier videos, and you can find the link to that video in the description. Note that recursive methods are always more expensive in terms of performance and memory usage. Recursion's only advantage is that some algorithms can be expressed more elegantly using recursive techniques. Prime numbers are those integers that have only two factors, namely 1 and itself. In other words, if a number is completely divisible by a positive number other than 1 and itself, it's not a prime number. Also note that numbers less than 2 are not prime. This is because numbers less than 2 are divisible by at least 4 divisors, namely 1, itself, -1 and minus itself. So in this diagram, n is the number to be tested for being prime. The red region denotes numbers less than 2 or less than or equal to 1, and these cannot be prime numbers. So, if we check for divisibility by all integers from 2 to n-1, where n is the number to be tested, and we do not find any divisor, then it means that n is prime. But if we do find a divisor between 1 and n, it implies that there are at least 3 divisors, considering that each number has 2 divisors, 1 and itself. Our objective is to make a method isPrime which accepts 2 arguments, number to be tested and the divisor. Our first divisor will be 2. Inside the function, we'll check if the number is less than 2, we'll return false, as numbers less than 2 will have 2 or more factors, as we discussed a few minutes ago. If the number is divisible by the divisor, it's at least the third divisor, implying that the number is not prime and will return false. If the number is not divisible by the factor, we'll make a recursive call with the value of the divisor increased by 1. And if the divisor reaches n without finding a factor, we'll return true. Now let us translate this logic into code. So we'll want to make a function which will check, that is, the return type will be Boolean. We'll call the function isPrime and then we'll pass our argument. Our first argument is the number which we want to test, and the second argument is the divisor. Once inside the function, we'll check. Please understand, our divisor is starting from a certain value, that is 2, and we'll keep on increasing it. So if the divisor reaches n, it means that the number is prime. We didn't found any defactor in between, that is from 2 to n-1. So if divisor equals n, we'll say return true. If that is not the case, we'll check whether the divisor which has been passed is a factor of n or not. So if n modulus divisor is equal to 0, that means divisor is a factor of n. And please note, we are not starting from 1, we are not going till the number. If there is any divisor in between, that has to be at least the third divisor. So if we are getting the third divisor, then it cannot be prime, so return false. And finally, at the end, we'll make the recursive call, that is, we'll say return isPrime, and we'll pass the number will remain as it is, but the divisor will go up by 1. We'll say divisor plus 1, and that's how the recursion goes. Now there is one more thing, like we are wanting to test whether a number is prime or not, and it is slightly counterintuitive for the end user that why we have to pass the divisor. So in order to lessen the burden of the end user, what we'll do, we'll have one more wrapper function, that is, we'll overload the function isPrime with only one argument. That is, if the user wants to check for a number whether it is a prime or not, he'll directly call this function isPrime with a single argument, And from within this, we'll make the recursive call. That is, hold on, we forgot one more thing. If the number is less than 2, it cannot be prime. So that also we'll place over here so that it is not checked every time. So if n is less than 2, we'll say return false. Otherwise, we'll make our actual recursive call. That is, we'll say is prime. And then we'll pass our two arguments. The two arguments are the number and the divisor, and obviously we are starting from 2, so we'll pass 2. This takes care of the main part. Now let us have something in the main to test whether or not our function is working properly. And for that, what we'll do, we'll make the program to display the number of primes in a certain range. So let's say I want to start from -5. I want to go till, let's say, 15. And then I increase the value of I by 1 each time. And then we'll actually print all the numbers which are in the range. So we'll say is prime I. That is, if I is a prime number, we want to display it. System.out.print. I want to print the number side by side, so I'm not using println. And then we'll say I plus, and we'll give a space in between. And when the whole loop is over, we'll have a new line. So system.out.println. So if this program is working properly, it is supposed to give all prime numbers from -5 to 15. I am taking negative numbers also so that we can check whether it is working properly or not. So let's run the program and see the output. So if I go over here and I run the program, there we are getting 2, 3, 5, 7, 11, and 13, which is correct. For better understanding, let us animate this program once in Gilliot. And in order to save my time and your time as well, I'm only checking for whether or not 5 is a prime number. So compile, and then there it goes. So first main will be initialized, and once we are inside the main, then the actual thing will start. So args created, main called, and then we are starting with the value 5. So is 5 less than 2? No. We'll go to the else part. We'll again make the recursive call, and this time the divisor is 2. Then we'll check whether the divisor is equal to n. Have we reached n without finding any factor? No. We'll check whether it gets divided by the divisor. 5 is not divisible by 2. So we'll go to the else part. This time again the recursive call will be made and divisor will be +1. That is, now we'll check the divisibility by 3. Again, we'll first check whether or not the divisor has reached n without finding a factor. 3 is not equal to 5. We'll go to the else part. Now we'll check whether 5 is divisible by 3 or not. It's not. So again, we'll call the recursive function. This time the divisor becomes 4. Again, we'll check whether 4 is equal to n or not. 4 is not equal to n. We'll again make a check for divisibility. Whether 5 is divisible by 4 or not. It's not. And then we'll make the recursive call again. This time the value of divisor will be 4 plus 1, 5. Note that this time we have reached the number and we haven't found any factor yet. So this time the condition on line number 14 will give us true. So no factor found from 2 to n minus 1. We have reached the number, will return true. And this true will be ultimately passed on through all the recursive calls. See, this is being passed up to the main. And then main, inside main, that is on line number 5, we'll be displaying is prime when it finally reaches the main. There we go. So that's how this program runs. Even though the program is working, it's giving correct output, there is still a scope for improvement. In fact, there is a lot of scope for improvement, and we'll see how. Now let us attempt to improve the program. Notice that 2 is the only even prime number because other even numbers are at least divisible by 1 itself and 2. Another way of looking at it is that even numbers other than 2 are not prime. So if we check for 2 separately and then the number is even, we can straight away conclude that the number is not prime. So essentially, by this even odd check, we can bring down the number of divisibility checks by half when the number is even. Compare it with the previous solution. For the value of 100, the previous solution will be checking for divisibility 100 times, and in this case, this will take just one check as 100 is even. Let us see another aspect of this problem for further improvement. Let us understand the next optimization with the help of an example. Consider the number 100. The list of factors are there on your screen. Notice that factors do not exist in isolation. Something multiplied by something gives us the product. So 1 into 100 is 100, 2 into 50 is 100, 4 into 25 is 100, and so on. You will also notice from the diagram that the first factors in the first column are increasing and the factors in the second column is decreasing as we move from top to bottom. Notice 1, 2, 3, 4, 5 is increasing over here and 100, 50, 25, 20, 10, etc. is decreasing. Now notice that the top half is essentially the same as the bottom half. 1 multiplied by 100 is same as 100 multiplied by 1. Similarly, 2 into 50 is same as 50 into 2. Further notice, and this is the most important part, that the repetition is starting after the square root of the number. So the number was 100, square root of 100 is 10, and beyond 10, the factors are repeating. Notice the divisors in red. We have indirectly checked for these numbers when we were checking for the divisors in the first half, that is below the square root. Since we have already checked for even numbers, there is no need to divide by other even numbers. Our first divisor will now be 3 instead of 2, and then we'll increase the divisor by 2 instead of 1. Note, in this diagram we are going from 3 to 5, we are not testing by 4. Similarly, we are going from 5 to 7, we are not testing by 6. And then we increase the divisor by 2 instead of 1. To divide by odd divisors only as even numbers other than 2 are not prime. Lastly, we'll consider the number as prime if we do not find any factor up to the square root. That is, we will not be going till the number now, we'll only be going till the square root of the number. Let us see the advantage of this optimization with the help of an example. Let us say that the number which we want to test is 101. 101 is odd, so our first divisor will be 3 and we'll go up to the square root in steps of 2. That is, we'll start from 3, then we'll go to 5, then we'll go to 7, then we'll go to 9, and note the square root of 101 is 10 point something, and we'll take only 10 because we are only considering integers, and once we reach root 10 we'll stop. If you compare it with our initial solution, you'll notice a substantial improvement. Just 4 comparisons instead of 101. Let us code these optimizations now. So let's begin with our optimization. If n is less than 2, return false. This is not going to change. We want to check for 2 separately. That is, we'll say else if n is equal to 2, then we'll say return true. Remember, 2 is the only even prime number. Then we check that if we are on line number 12, that is the current line where the cursor is, it means that the number is not 2. And if it is even, then we know that even numbers other than 2 are not prime. So if n modulus 2 is equal to 0, we'll say return false. And then finally we'll make the recursive call. But again, here also two changes are required. One, the divisor will now start from 3 instead of 2 because we have already checked for 2. And then we want the thing to go to up to a certain limit, and that limit is supposed to be the square root. So we'll pass the square root as the third argument. We'll say math dot sqrt n. So for smaller numbers, this might not be very relevant, but for larger numbers, this will make a huge difference. Now notice there is an error over here because there is no third argument over here. So we'll add the third argument. We'll say int, let's call it limit because that is what it is. And here also we'll keep on passing the limit. And then we have to add a test for checking that limit. That is, we'll say that if instead of this, we'll say that if divisor is more than our limit. Please note we are not saying more than or equal to because equal to might be the last divisor. So if divisor is more than the limit, then we'll say return true. Otherwise, we'll proceed like we were doing earlier. And in order to skip the even divisors, instead of saying divisor plus 1, we'll go in steps of 2 and we'll say divisor plus 2. Let's run this program and see whether we are getting the same output or not. So if I run it, there we are getting the same output what we were getting earlier, that is 2, 3, 5, 7, 11 and 13. Notice this was our output earlier. This is still our output, but now the program is running much faster. Now let us animate this program for better understanding, and we'll animate this for is prime 101. That is, we are going to check whether 101 is a prime number or not. So the initial value of n is going to be 101. Let's begin. So the first value is 101, which is passed to the method. We'll check whether 101 is less than 2 or not. Remember, numbers less than 2 are not prime. It is not. Now we'll check whether it is equal to 2 or not, because 2 is the only even prime number. This is also not equal to 2. Now we'll check whether it is even or not. And if it is even, we'll straight away say return false, but it is not even. So now we'll make a recursive call. The value of n will obviously remain the same, but now we'll start dividing by 3. That is, the first value of a divisor will be 3, and we'll go up to the limit, which is the square root of the number. Square root of 101 will be 10 point something. So that 10 is converted, that 10 point something is converted to 10. The function is called. And now we'll check whether the divisor is more than the limit. No, it's not. 3 is not more than 10. Again, we'll check for divisibility. It is not divisible. So we'll again go for the recursive call. Divisor will increase by 2. Limit will remain the same because the number is not changing. So we'll again pass 10 as the limit. Now we'll check for divisibility by 5, but before that we'll check whether or not we have crossed the square root. We have not crossed the square root because the square root is 10. Again we'll check for divisibility. It's not going to divide. And we'll again make the recursive call. So here we go. 5 plus 2 is 7. So the next divisor is going to be 7. Again, we'll check whether 7 is more than 10 or not. 7 is not more than 10. We'll proceed on to the next if. We'll check for divisibility. It's not going to divide. And then again, we'll make the recursive call. So no division. We'll again make the recursive call, this time with 9. Now 9 is also not more than the limit. The limit is 10. So we'll check for divisibility once again. (101) is not divisible by 9 also because it's a prime number obviously. We'll again make the recursive call one last time, and this time the divisor will be 9 plus 2, 11, which is more than the limit. So here we call the function again. The values are passed. And this time we'll check whether 9 is more than the limit, or sorry, 11 is more than the limit or not. 11 is more than the limit, that is 10. And then we'll return true. And this true will be returned to the function which called this, and this will keep on happening right up to the is prime function and then up to main, and this will finally display true. So this is how it goes up the call stack. And finally it will reach the is prime, and from is prime it will reach main and it will display true. In conclusion, we have explored two different approaches to implementing a primality test in Java. The regular factorization approach works by iterating through all possible factors of a number, which can be time consuming for larger numbers. On the other hand, the optimized approach reduces the number of iterations needed by checking only up to the square root of the number being tested. We have also seen how recursion can be used to simplify the code and make it easier to read and understand. By breaking down the problem into smaller subproblems, we can avoid repeating the same code over and over again. Overall, both approaches have their advantages and disadvantages, and the choice of which one to use depends on the specific requirements. For examination purposes, the shorter version is usually sufficient, but for real-world use cases, the latter is preferred. That's all for now. See you in the next video. Your feedback is valuable to me. I want to make sure that my videos are clear and helpful. If you have any questions or suggestions for improvement, please don't hesitate to leave a comment or send me a message.